If we're looking at velocities, remember velocities are not just displacements. Velocities are displacements over time, or the ratio of displacement to time. For example, if we return to our original values here, and we talk about the average velocity, it equals the displacement divided by the time taken. And if you want, that is the end point, or end xy, let's make this a little more consistent, minus the start xy, divided by the end time minus the start time. And that relationship we've already studied all the details of. We're just putting them together into a new package here. So we'd have our cos of 1.6, I'll put that in a second, and sine of 1.6 minus the cos of 0.5, sine of 0.5, just highlighting those in different colors. So end minus the start. And then this time we're going to take that and we're going to divide it by the end time, 1.6, minus the start time, 0.5. And if you take a look at the units, which is always a helpful thing to do in parallel here, all of the units in the numerator here are about x's and y's, they're about meters, they're about space, whereas the time values in the denominator are all in seconds. So what we would be computing here is something that has units of meters per second, which again naturally feels like a velocity. Now notice that's an average velocity. When we are traveling along the circle, we're actually traveling at some points more northwest than that, or more north than that. Towards the end, we're pointing more west. We're averaging over that whole time span with this calculation here. We're simplifying all the middle stuff and just saying, on average, if we ended here and started here, what is the velocity on average over that entire time interval? Of course, in calculus, we're interested more in the idea of velocity at an instant, so that's what we're going to work up to next. Of course, we have to make a quick distinction here, which is especially relevant in vector quantities. So we just found a velocity vector here, or an average velocity. And the distinction we're going to make in this class is that velocity is a vector, and so has components, whereas speed is going to be the magnitude of the velocity. For example, if we had a velocity vector that was equal to 1,3 meters per second, corresponding to a vector like this, 1,3, roughly like so, then the speed is equal to the magnitude of that velocity, which is that Pythagorean formula, the square root of 1 squared plus 3 squared, square root of 10 meters per second. Same units, but the velocity has richer information, but sometimes the speed is actually more relevant for what we're looking at. Velocity will be the vector component, and speed will be the magnitude of that vector. Now let's return to our second example, where we had 2 points, time at 0.5, and a second point at time 0.5 plus some later moment. So we had our point here on the circle, and that was r of 0.5. And then we move, just imagine here a very small time, because we are going to let that time interval go down to 0. And then we ask, what happens to the average velocity function as the time interval gets smaller and smaller? Notice that this is the same displacement we had before. The only difference is we're now taking that and we're dividing it by delta t. So we get displacement divided by time interval. So think a moment about the three options here, pause the video if you like, and see which one seems to match your intuition about the velocity vector as the time interval gets smaller and smaller. All right, here we see a bit of a tension. So one thing is true, the displacement vector does get smaller and smaller, that's true. However, that's being counterbalanced by an opposite force, if you like, in the mathematics. We have a smaller and smaller delta t, which means that the 1 over delta t is getting bigger and bigger. So this is also true. And quite frankly, one of the surprising, miraculous results of calculus is that if we're talking about a particle moving around in a reasonable way, then as we take a ratio of these smaller displacements divided by smaller delta t's, that ratio actually stabilizes, and we end up getting a vector that stays roughly the same length. If we talk about the average velocity from here to here, or the average velocity in a time interval that's half as long, well, nothing much is changing. In particular, nothing much about the velocity is changing over those small time intervals. What we're sneaking up on here is the idea of the derivative. If we take smaller and smaller time intervals and look at the change in displacement, or just the displacement rather, change in position, over the time interval, as the time interval goes to 0, this approaches the instantaneous velocity, and that is what both Newton and Leibniz originally defined as the derivative of a function. Only now our function has two outputs and a single input, so it's going to be a little different than what we've seen before, but we're going to see tons of parallels between earlier derivative calculations and vector value derivatives. We just need to investigate the details.